Hi, I'm Yang Hai, and I'm going to present our CVPR 2023 work, Rigidity-Aware Detection for 6D Object Pole Expectation. This work is done with Ray Song, Jiao Jiao Li, Mason Sutherman, and Jingling Hu. Most recent 6D Object Pole Expectation method first uses object detection to remove the object region for better performance. However, the general object detection datasets exhibit smaller occlusion, and the standard object detection methods assume the central box depicts the object of interest. This makes them ill-suited to handle cluttered synthesis and produce poor initialization for 6D object pole expectation. By contrast, we propose a rigid-aware detection method, which is effective in these challenging scenarios and provide more robust 2D box for subsequent 6D regression, yielding more accurate pole estimates. Our network architecture follows a standard one-stage detector with feature pyramid network as a backbone. The positive feature cells or the feature map are supposed to be classified as the associated category and regress the corresponding box, while the negative cells should be classified as the background category. During training, we first compute the visibility for every pixel within the bounding box, which we use to get the sampling of positive cells without any mask annotations. During inference, we combine all the local candidate predictions to obtain more robust final result. We find that sampling strategy is the key for training the object detector. The standard strategy treats positive samples around the object center. Instead, we propose to use a visibility-guided sampling strategy to discard the occluded regions and encourage the network to be supervised by all visible parts, which can explore the object rigid property. As a result, our method can yield more accurate detection than the standard strategy. To evidence the rigid property, that is, all visible object parts can provide a reliable prediction of the entire bounding box. We train a standard one-stage detector with different sampling strategies. Center and center plus respectively stand for F-cos V2 and ATSS, while visible is to randomly choose 10 positive samples within the ground truth object mask. On the general detection dataset COCO, all the methods perform stick rate with an increasing distance to the ground truth box center. In contrast, for the rigid object dataset YCP video, the feature cells that are farther away from the center can still provide robust prediction, while the center-based strategies still exhibit similar phenomena as the COCO. This strategy requires a ground truth object mask, which is hard to annotate. To overcome this issue, we deploy the classical dissonant transform to approximate the visibility of each pixel in the bounding box. We first place a seed on the boundaries of the bounding box, and then compute a minimal barrier distance between every pixel and the seeds. Finally, we obtain the distance map to build the visibility of each pixel. For center-based sampling strategies, based on the assumption that only the region around the box center can yield robust prediction, NMS is typically used to select the candidate with the maximum confidence within a local area. However, other candidates can provide reliable predictions in our training strategy. Thus, we first propose to fuse other candidates within a local area to a more robust one. Here we show qualitative detection and pole results of different datasets. As shown, our method is more robust than F-cos V2 and produces accurate pole estimates after using PFA poles. Our paper and code can be found here. Thanks for watching.